Okay, hello everyone, I'm Scott Wen Tau Yih from Microsoft Research, and today I'm going to talk about our paper, Type Tensor Decomposition of Knowledge Bases for Relation Extraction. This is joint work with Kai-Wei Chang, Bishan, and Meek, and Kai-Wei was our intern last summer, and he did the most work in this paper, and Bishan was our intern this summer, and she helped on some of the experiments. Okay, so by storing properties of millions of entities as well as relations among them, we have seen that large-scale knowledge base captures world knowledge and has been useful resources for different NLP applications such as semantic parsing for question answering and also information extraction. And then as you already saw from the previous talk that a knowledge base is never complete, so you can always find something that the knowledge base doesn't know. And you can choose one method, which is, try to extract more information from the news corpus or from other data collection, and then trying to get more facts. Or you can try to see that we can, do the old AI fashion way by trying to infer recent new facts using the existing knowledge in the knowledge base. So to model this kind of multi-relational data, typical statistical relational learning usually are not very scalable, and it's usually difficult to handle a large-scale knowledge base. So this kind of scalability issue also is the trigger of the recent development of the path ranking methods, while they basically apply random walk on knowledge graph. Now today I'm going to talk about the third category of methods, which I call knowledge-based embedding. It's very efficient in the runtime, and it has shown in some cases that it provides better prediction accuracy. Okay. So the framework of knowledge-based embedding can be described as follows. So each entity in the knowledge base is going to be represented as a three-dimensional real vector. And when we try to predict whether two entities have a particular relation, we just apply a simple function on the vectors that represent those two vectors. For example, the function could be a linear function or just a bilinear function. And knowledge-based embedding has been a hot topic recently, and there are quite a few models have been proposed. Those models are basically trained on existing facts or the E1 or E2 triples. Usually the relational domain knowledge available in the knowledge base, such as ontology, is typically ignored. So what I mean by relational domain knowledge, let me give you a couple examples. The simplest one is probably the type constraint. So let's say that the E1 and E2 may have the Bohmian relation only if the first argument E1 is a person and the second argument is a location. And sometimes the relational domain knowledge can come from some rules. For example, if you say that E1 is a child of E2, this kind of things can only be true if both E1 and E2 are persons, and also E1 is younger than E2. So in this work, we propose a type tensor decomposition for knowledge-based embedding. In the end, each entity is going to be represented as a vector, and each relation is going to be represented as a matrix. And the relational domain knowledge we incorporate here is the type information and constraints. We do that by kind of manipulate the loss function, so only legitimate entities are going to be included in the objective. And there are several benefits of leveraging type information. As you can see later, that the model training time is substantially faster, which make this algorithm highly scalable to handle large database. And also, you'll see that we also have a better model in terms of prediction accuracy. And in the end, I'm going to show one application to relation extraction. Okay, so in the remaining of my talk, first I'm going to give you some background on the paradigm of the knowledge-based embedding using tensor decomposition methods. Then we'll describe our methods in more detail, followed by experiments and the conclusions. Okay, so a knowledge base can actually be viewed as just a collection of subject, predicate, object triples. Again, Obama is a very popular example, so you can see that Obama was born in Hawaii is one of the triple over here. And so this collection of triples can be encoded very easily using a three-way tensor, where we will have m different slices. M is the number of relations, and each slice is going to be an m by n square matrix, where n is the number of entities. So let me use this particular relation as example. So if you want to know whether two entities have a particular relation, such as born in here, we just need to look at the particular, the corresponding slice over here, and then we check these two entities, Obama and Hawaii over here. And entry 1 here basically indicates that, okay, Obama was born in Hawaii, so these two entities in this relation is a known fact, so we know it's true. So the meaning of entry 1 is pretty clear here. Interestingly, if the entry is 0, it actually can mean two different things. It could mean that it's incorrect. So this triple is just wrong. There's no such thing. Or it could be that it's possible, but for now the knowledge base just doesn't have this knowledge. It doesn't know whether this triple is correct or not. Okay. So just like you can use SVD to decompose a matrix, and there are corresponding high-order method for decomposing tensor. So in this case, each slice of tensor, which is a matrix here, we can also decompose it into 3 parts like this, where the A's are actually the latent representation of the entities, and also the RK is a small embedding matrix that capture the relation. And the objective function here consists of 2 terms. The first one is the typical reconstruction error, and the second one is just the regularization term. And the method here is basically the race code model proposed by Nico et al. In 2011. Okay. So once we have the entity, once we have the vector representation for the entities and also metric representation for the relation, and then when we want to predict a particular triple, whether it's these two entities have a particular relation, the process is very simple. You just need to take the corresponding vectors and also the matrix and then multiply them together. Okay, so now let me talk about our proposal of using the type information in this tensor decomposition framework. So remember that a 0 entry could mean 2 different things. Okay, so the idea of using the type information is really to help us to get rid of those entries that we know they are false for sure. Okay, so let me again use the born-in relation, for example. We know that the born-in relation for the first, for this kind of relation to, for this kind of text to be true, the first argument has to be a person, and the second argument has to be a location. So, which means that only this kind of square matrix over here have the chance to be correct. And all other zeros or the space here are just incorrect. And so ideally, we don't need to worry about that. Okay. So here, when we look at those, that just focus on the reconstruction error and ignore the regularization term for now. So having this observation, then it becomes very simple. So we just ignore those white space, and then the objective function here only has this square matrix over here. Okay. Sorry, sub-matrix over there. Okay. So and then okay, we modify the object function. Now let's see how we can adapt a training method to really optimize for this object function. So first, let's look at the original methods for this tensor decomposition framework. So the standard procedure is called the alternating least squares method. So conceptually, it's pretty straightforward. So the first step is that we fix RK and then update A. There'll be something like this. And then the next step is fix A, update RK. Something like that. So, and then we do it iteratively, okay. So even though it looks pretty complicated, it's actually just some linear algebra operators on those matrices. Okay. And how do you adapt that? pretty straightforward. We just replace the corresponding matrices with the submatrix that which I just showed in the previous slides. Okay. So finally, let me give you some analysis on the computational complexity. So without the type information, the original risk code complexity is n times r squared plus p times r, where n is the number of entities, p is the number of non-zero entries in the knowledge base, and r is the dimensions of the projected entity vectors. And with the type information, really the difference is we now, instead of having n, we have the n bar here, and where n bar is the average number of entities that satisfy the type constraint. And empirically, we found that the ratio between n bar and n is roughly 0.06 over here. Okay, so that's basically our proposal, and then let's see how those things, how it works in some experiments. Here we have two sets of experiments. The first one is about the knowledge base completion, and the second one is its application to a relation extraction task. Okay, so in order to show that the method is really highly scalable, so we use the never-ending language learning database, NEO, to create a large data set. Essentially what we do is that we take the one particular version, version 165 as the training data set, and then we use the new facts discovered in the later iterations as the development set and also the testing set over here. And then in this table, you can see some of the data statistics of this training set. I just want to mention that, so we have, in terms of the number of triples over here, we have 1.8 million triples, which is, I think is the largest in the publicly available data set that have been used for knowledge-based embedding experiments. Okay, and then we test this model on two different tasks. One is called the entity retrieval. Essentially, it's like providing, given one subject entity and also the particular relation, we want to find the object entity over here. And the second task is what we call the relation retrieval. So here is, given a pair of entities, we want to know, okay, whether which relations these two entities have. In terms of baselines, we specifically choose two. The first one is, of course, the original tensor decomposition model, RISCO. So this one doesn't really use the type information. And the second one is the Chang model. You can say it's kind of like a neural-based, knowledge-based embedding model. And they basically, instead of using a matrix, they represent the relation as a vector as well, and then the relation is essentially the difference between the two argument entities. Okay, so now let's first look at the time reduction. So on this slide, you can see two bars. The first one is the original RISCO method, and the second one is our type tensor decomposition proposal. And the unit here is hours. So we train both models using 10 iterations. And because we leverage the type information, so we filter out probably around 96% triples that have the incompatible types. So as a result, we enjoy 4.6 times speed up. So originally probably 20 hours, and then now we reduce it to 4 to 5 hours in terms of model training time. Then if you compare to the Chang model, which is already pretty efficient, you can see that the gap is actually even bigger. So here we actually have more than 20% speed up compared to the Chang algorithm. So having, being able to train the model in a short time is nice, but if the model is, it doesn't really predict well, it basically loses the purpose. So it's important to look at the prediction accuracy as well. So here for the entity retrieval task, you can see that our method still is better than the other two baselines over here. So here the evaluation metric is a ranking method, mean average precision. And for relation retrieval, we also have our method also performs better than the other two baseline methods we compared here. Okay, so now let's see how these things can be also used for relation extraction. So relation extraction in general is kind of like, you're given the system some kind of text document, some kind of document, and then hopefully you can have the system to extract some facts from the text in the documents, such as the example shown on this slide. So last year, Red Dot and I proposed a very different relation extraction method. So essentially the idea is to use the metric factorization. So in their setting, they kind of mix the entity pairs extract from the text and also entity pairs from existing knowledge base. And then the construction is that for each row in this matrix, they will use the entity pair, the candidate entity pair that they want to consider, they want to find the relation. And each column is the relation. So maybe for some entity pairs, you already know the relation. And by this construction, they use the metric factorization method, things like collaborative filtering, to identify, to do this kind of prediction. So we use their data set to do the experiments. So their data set basically is the entities in the New York Times corpus, and also those entities are aligned with some free-based entities. So in this set of experiments, we constructed a tensor with more than 80,000 entities, and there are 1,652 relations. The type of information we actually get that from freebase and also using a name entity recognizer. The type of constraints are just derived from the training data. So the task here is to identify freebase relations of entity pairs in text. There are actually 10,000 entity pairs, but only 2,048 have both entities in freebase. So in this case, we just follow their evaluation setting. So we use the same code and use the weighted mean average precision on 19 relations. So if we actually evaluate only on these 2,000 freebase entity pairs, I have to say that if we just use our method itself, it doesn't really outperform existing methods, but we still find a nice way to use our system, which is, it actually provides complementary information to existing system. So by adding that with the radar system, we can see that there's a slight improvement on this set of testing data. And if we actually evaluate using all the 10,000 entity pairs, and we can see a bigger jump over here. Okay, so in conclusion, in this talk, I present TRESCO, which is a knowledge-based embedding model using tensor decomposition. So the key difference here is that we leverage entity type constraint information. It has several benefits for doing that. First, I showed you that we have a much faster model training time, and which makes this algorithm highly scalable to handle large-scale knowledge base. And also, in terms of prediction accuracy, our model actually performs better. And I also show you one particular application to relation extraction. And for the future, we would like to capture more types of relational domain knowledge, not just the entity type constraint. And also we are thinking of supporting more sophisticated and inferential tasks using this kind of knowledge-based paradigm. And that ends my talk. Thank you very much.
Again, we have a lot of time for questions. Because people practiced well.
Hi, so these knowledge bases contain both errors and have missing information, which is also true for the typing constraints. So just curious if you did anything special to handle those issues.
We kind of ignored that at this moment. So even though I totally agree that what you say, that a knowledge base is messy, so they have contents error. So the type of information, empirically, when we run the experiments, we essentially just check the training set. So if there's no, we look at the triples there, and then to check the types. So, and use that as ground truth. I mean, and then incorrectly, you can probably also relax that a little bit. So as long as with high probability that those types are consistent, and then you can accept that. But to your original question, whether that kind of noise affect this result or not, honestly, I don't know, and probably not, because even though there's noise, it's actually not huge. And also, I guess it also depends on what kind of knowledge base you're talking about. So for knowledge base that are created using automatically or semi-automatically, yeah, it probably will have more noisy data. But for things like free base, probably it's better. Yeah.
More questions?
Yeah, nice work. Have you tried to evaluate whether your training gets stuck in local minima?
We didn't actually. Okay, so the optimization problem is not convex. So what you say is possible, but empirically it works. It seems to work fine. So we actually didn't really have any specific concern about that problem. And even for the tensor methods, we actually even just fixed the 10 iterations, and it usually converge fine. Of course, I have no idea whether that's a local or global, or whether the difference will be a lot or not.
Okay. I have one. I understand you have to use Freebase for papers because it's available to the community. Microsoft has a large database, Satori. So did you try these experiments on Satori, which is?
Not yet, but I do have that in mind because I also work for Microsoft. And
Yeah.
So that's why we actually care about the scalability issue.
Yes.
Yeah. Yeah, we haven't, but yeah.
Thanks again.
All right, thank you.